Howdy, today I'm going to demo Lab 8, and in this lab we created ALU control module and the data memory module, as well as next PC. So I will go ahead and go through these files and talk about them. So first off, data memory module, this is this bar. A diagram so I can explain it better. Yeah, okay. So So the objective for this module was to create this data memory register that has inputs from the ALU, as well as memwrite and memory flags. Both these can't be high at the same time. And we also have a read data to this mux. So we have to keep track of this mux. Actually, this will be going in a single cycle processor module. We just need these the outputs will be read data at 64 bits, and then also our address. So when we're so when we need to pull the address of the register to like a store or load, and so input is when we are writing to memory, or this memory flag, memory write flag, and then we also have a clock to hold the memory as it's a register. So over here, I initialize an array of memory. So 64-bit memory net with a depth of 64, so each register or each address will have a 64-bit depth. And then so we use this for loop. And yeah, so this for loop will initialize our memory to 0. And now in our always block, we will be at the positive edge of the clock, we always do memory reads. And at the negative edge of the clock, we always do memory writes. And so this non-blocking statement, read data, delay of 20. And so this is our output, read data, and then the memory at the address specified. So this is going to be the input address. And in the case of memory write, we will be writing the inputted write data to this memory block that we declared up here at the address. And both these delays are 20. And so let's go ahead and run this program. So we're going to need output file, data memory dot v, and then our test bench test, and the data memory test dot v was provided for us, so we can just go ahead and run this and see if our tests pass. So yeah, initializing read address 14 hexadecimal, read address at F0, read address at CC, and yes, so these are these tests, and all tests have passed. So, yeah. I wonder why the test bench didn't include any writing, but that was the one that was provided. Maybe wrong. Okay, now let us test our next program, or module, I should say. And in this one, we developed this ALU control module. So in this module, we have an output of ALU control, an input of the ALU, the 2-bit opcode, or the ALU op, and then the 11-bit opcode, which is standard. And so based on this chart, I mapped all the logic. So yeah, we're going to be using always block again just to use behavioral Verilog, although we don't have a clock. Clock was just for the register in the data memory. So in this module, we will be defining the 11-bit opcode input, 2-bit ALU op input, and then a 4-bit ALU control output called reg, so we can put that in the test bench. And yeah, so always at a star. So in the case of ALU op being just a 0, 0, it's basically don't care, and this would just basically means that it's a D-type instruction like load, store. And in the case of this, we don't even care about the opcode itself. So yeah, in this case, we just immediately set it to 0, 0, 1, 0, 4-bit. In the case of a conditional branch, we will be checking if the ALU op is a 0, 1. And if it is, then we know what ALU control is set. And this is a delay of 2 nanoseconds. And then, so else if none of these, it has to be an R type. So yeah, in this case, we will be doing else if, and then we will check for the actual opcode in this case, so we can assign like the actual like R type instructions. So we have add, subtract, and or, and these aren't immediates. These are just although they would work with immediate instructions. Okay, we can go ahead and run this one as well. So we called it ALU control. And ALU control test. .v. And key. So yeah, all tests passed. First test, the ALU input is 0, 0, so that takes us to the D-type instruction load store. Second test is parachute branch, and then all these are R types. Actually, some of these might not be R types. Yeah, all tests pass, and yeah, good on that one. It's provided. Okay. Module 3 is the next PC logic. This one was an interesting one. Yeah, in this module, we really look to get this part of the Datapath done, and so we have some pretty basic logic. We don't care about the mux right now, but we do implement this scan gate, and I think we also implement the roll gate. Yeah, so scan gate, which takes inputs branch, and then the ALU if 0, and then we OR that with unconditional branch. But if it's branch, then unconditional branches obviously don't care. So XPC. So this is quite simple. So our inputs are current program counter, the sign extension, which I think in this case is the shifted. Yeah, so it is the shifted sign extender. The branch flag, ALU 0 flag from the ALU, and the unconditional branch flag. And yeah, our output is the 64-bit program counter. So yeah, behavioral Verilog once again. If unconditional branch or branch and ALU 0. So in the case of an unconditional branch, our branches don't care. And So we have a 3 nanosecond delay in this case, where our next PC will just be the current PC plus sign extended immediate 5. I think this should be shifted left too, but I may have implemented that. But I think this is the correct implementation for this one, although it might not be correct. I will have to check my lab note actually. Yeah, so that is not the correct implementation. Let's go ahead and fix this. All right. So yeah, this should be the correct implementation for this, and then else if we're not meeting any of these criteria, that means we're not branching at all, and in that case we're just going to the next PC, incrementing by 4 to the next instruction. So in that case we add 4 to our PC, our 64-bit. Let's go ahead and test this as well. PC test. Okay. So we have some test pack, regular counter pass. So we don't branch, we don't have ALU 0. Okay, so this implementation is correct, although in the case of our branching, we do not pass on the conditional branch. Okay, I think this might be correct. Might Yeah, so the explanation for this is I think the test bit input for the sign extent, the 64-bit sign extent is already shifted in this case. So. But yeah, that should be my demo for this lab, and I can go ahead and actually show some waveforms. The ALU control. And yeah, so we have our inputs, the opcode, the ALU op, and yeah, this is our initial delay of 2, and then from there we get our correct ALU control. So after this, yeah, so this will be our data memory, and in this case we have the clock of 50 nanosecond. Clock would be frequency of period is 100 nanoseconds, so 1 over 100 nanoseconds. 10 megahertz. And yeah, finally, our next PC counter. And yeah, that is it for this demo. Thank you so much.